All right, so we're going to go ahead and take a look at exponential growth and decay models today from real life scenarios. Okay, from real life scenarios. So I need you to open up your Desmos scientific calculator and your graphing calculator, just because we're going to be making use of both of them today as we kind of take a look at how to come up with some values. So let's start by just refreshing ourselves on how to change a percent to a decimal, because when we're working on exponential functions, they give us numbers in percents, okay? And we actually need them as decimals. So one of the things that I want to kind of just throw out there is exponential functions are probably one of the most commonly seen or used functions other than linears in the real world. And it's used pretty much anytime we're talking about money. And there's actually another place where we've seen it pretty dramatically in the last year, and that's with the coronavirus, because exponential growth is why the virus has spread as quickly as it did across the world. So we'll kind of look at how this works today. But again, anytime we're talking about money with interest, like loans or credit cards, or we talk about how things depreciate in value, or we talk about how something grows exponentially, like viruses and the populations and that kind of thing, that is almost always exponential. All right, so let's start by remembering, how do we change from a percent to a decimal? If you remember, that is moving two places, which means I'm dividing by 100. So if you think about what happened here, I moved it two places to the right. So this would be 0.032. Decimal is here, 1, 2. So this would be 1.25 because that's more than 100%. 0.512 would be 0.005. That one is a really small piece. And if I just have a regular percent, it's going to be 0.12. So remember, you can either move it two places to the left, or you can just divide by 100. Okay, so here's some words that we need to know, because this is going to determine whether or not we're going to grow or we're going to decay, because it makes a difference in terms of our formulas. So some of the words that mean growth that we're going to see in our problems, if it tells us it's increasing or it's going up, that's going to tell us it's a growth. If we see something about interest, that is also growing, okay? So that means we are adding on to our total quickly. Now, decay, that means dropping. So depreciate is probably the big word we're going to see. We might see down, decrease, lose value, dropping. Any word that means going down or dropping in value is going to tell us that we're going to be subtracting our percent. Okay, let's take a look at our formulas. So we have y equals or f of x equals, the same thing. Remember, f of x is the same thing. A times 1 plus r to time t, or we have a times 1 minus r to the t. So decay, we're going to subtract. Growth, we're going to add. So take a minute, write down these two formulas. Remember, it can be f of x, it's the same thing. And we're going to go ahead and use them in our problems. All right, so here's our first problem. So the prize for a radio station contest begins with a $100 gift card. Once a day, a name is announced. The person has 15 minutes to call, or the prize increases by 2.5% the next day. So when we're solving an exponential growth and decay problem, we're looking for like three things: an A, an R, and a T. Okay, an A, an R, and a T, because that helps us write our function. So the A is the starting point. So how much is this card when I begin? Well, it's $100. So I know my A is 100. Now the R, that needs to be as a decimal. Okay, so I actually need to change that percent to a decimal. So 2.5% is actually 0.025. So I need this number as I am going to be moving forward. And so far, I don't know what my t is, so I'm going to have to come back to that. So let's go right and write our function. We start with 100, and we have 1, and this is a growth. So I'm going to use plus 0.025, and I'm going to use t for time on this problem when I write my function. But when we use our calculator, we are actually going to use an X. Okay, we're going to use an X because it doesn't understand what a T is unless I tell it f of t. Okay, let's keep reading. How much will the gift card be worth if no one wins after 10 days? Well, that T is 10. Okay, so I actually need to evaluate 1 plus 0.025 to the power of 10. So let's go ahead and get our calculator ready. And let's put that in. So we have 100, so 1 plus 0.025. Remember, watch your decimals there. And I need to have a power of 10. So remember, you can either do power with this a to the b, or I can do shift caret, which is above the 6, to be able to get that to the 10, and then I put in my 10. And you'll see that I have $128. Now, this is money. So 0.008 means that I'm going to round to a penny. So this is actually $128 and a penny. So after 10 days, that gift card has increased $28.01. Okay, let's look at the next one. So we have a fully inflated children's raft for a pool that is losing air. Okay, so losing is important because that means it's going down. It's going to be a decay for every day. So it originally contained 4,500 cubic inches of air. So I know that I'm starting with 4,500. And it says it's losing 6.6%. Well, that as a decimal is 0.066. So my function so far is 4,500 1 minus, because it's decay, 0.066. And do I know what my t is yet? Well, if I keep reading, it says my t is 7 days. So I'm going to throw a 7 in here. And I want to evaluate that. So 4,500, 1 minus 0.066. And again, you need a power, throw in a 7. I see that I have 2790, so 2,790. We're going to round it to the nearest cubic inch. We're just going to ignore those decimals. So that's 2790 cubic inches of air. 2,790 cubic inches of air. All right, let's look at a car. So when we purchase a car, most of you realize that when you purchase the car and drive it off the lot, it's going to lose value the moment you walk off the lot. Now, there are certain cars, like a 1960 Shelby Mustang, that's going to increase in value, but most cars decrease in value. Okay, so this says Leonardo purchased a car for $18,995. It depreciates at a rate of 18% annually. After 6 years, Manuel offers to buy the car for $4,500. Should Leonardo sell the car? Well, let's see if we can come up with our function, and then we'll try to figure out what is the value at 6 years. So we have $18,995, and 18% is actually 0.18, and my t is going to be 6. Okay, my t is going to be 6 because it wants the value after 6 years to determine whether or not he should buy the car. So 18,995, 1 minus, because depreciation is subtraction, 0.18 to the 6th power. All right, so let's see what we got. So 18,995, 1 minus 0.18. And I need a power of 6. Well, my car at year 6 is worth 5,774 point. Let's round that to money. So decimal spots 2. 60 becomes 61. So my car is worth $5,774.61. So should he sell the car to Manuel for $4,500? No, he shouldn't. The car is worth more than $4,500 at year 6. So that would not be a good choice for him. Now, obviously, we don't know if it's got damage or that kind of thing, but just on the basis of the math, the car is worth more than $4,500. Okay, why don't you go ahead and hit pause, see if you can figure out what to do with this one. All right, so we got a rabbit population in 1 square mile area in the year 2010 was 300 rabbits. So that's my starting point. So I start with 300. The population grows at 23% per year. So 23% is actually 0.23, and I see it's growing, so I know that it's going to be plus. So 300, 1 plus 0.23. And do I know what my time is? Well, they give me 2030. So the one thing I have to realize, if they give me the years, I'm never going to use the years. I have to figure out how much time has passed. So 2010 to 2030, that's 20 years. So the 20 is what my time is. The 20 is what my time is. So if I figure that out, I have 300, 1 plus 0.23, and to the 20th, I see that I'm going to have a whole lot of rabbits. Now, we need to round appropriately. So I'm not going to have 0.18 of a rabbit. So this one I actually need to round down. No matter what the number was, I would need to round down to the closest rabbit, okay? Because I can't have 0.9 of a rabbit. That would mean he might not have ears. So there is 18,846 rabbits. Now, again, that's just the math. We don't know if there is predators out there who are reducing that population, but if it was just purely the math, there would be 18,846 rabbits. All right, so during normal breathing, about 12% of the air in the lungs is replaced after one breath. So write an exponential decay model for the amount of original air left in the lungs if the initial amount of air in the lungs is 50 milliliters or 500 milliliters. How much of the original air is present after 240 breaths? Okay, so let's go ahead and we're going to look at this one using the regular calculator and the Desmos calculator because I want you to see how you can use both of those. So I know that I'm starting with 500. I know that I'm replacing, so that's going to be a negative. It's going to be subtraction. So 0.12 is what I need to use. And 240 is my time. Okay, 240 is my time. So my function is 500, 1 minus 0.12. And I'm going to go ahead and make this an x and make that an x for our purposes of what we're doing today. I want to show you how to use the Desmos graphing calculator to come up with our numbers. So let's go ahead and figure out what we should be getting. 500, 1 minus 0.12. And I need 240 breaths. So you can see that I have something in scientific notation. So 2.37 times 10 to the negative 11, which means 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's how many milliliters of air would be left in my lungs of that original breath after 240 breaths, okay? So let's go ahead and look at the Desmos graphing calculator. So I'm going to go ahead and erase that, and I want to put in f of x equals, and I'm going to put 500, 1 minus 0.12, but I'm going to put it to the power of x, okay? And the reason I want to do this is because I want to be able to see a list of numbers. So I'm going to go to my table, I'm going to add a table, and I can see. Here's my table for that function. So at 0, it's 500. At 1, it's 440. At 2, it's 387. If I wanted to see how it decreases, I can keep putting in the numbers. I can even put in my 240, and I see the 2.37 times 10 to the negative 11th. Okay. If I wanted to know what it was at 50, I can put in a 50. So I can use the table to kind of evaluate where I am. So if I asked you, how many breaths to have less than 100 milliliters of the original air, what I can do is I can use my table. So I see that 4 breath is 299. 5 breaths is 263. I'm going to go ahead and go up to 10 breaths. I have 139. I'm going to change that to a 15. That's too much. What about 11? That's 122. What about 13? What about 12? So I'm between 12 and 13 breaths where I see that it hits less than 100 milliliters. Okay, so 13 breaths is where I would be. So sometimes we're going to want to make use of this other calculator, the Desmos graphing calculator, to kind of determine where something happens. Okay, so that is the first part of today's lesson. There is a second video today on compound interest. Please make sure you watch that because there are some different vocabularies and a little bit different formula that you have to be familiar with as you start your homework. If you have any questions, reach out to us.